Hello, I'm Cheryl Biswas. I go by Encrypted online, and I'm honored to be presenting at the Texas Cyber Summit this year. Welcome to my talk today, Invitation to Exploitation, Risks from Mass IoT Vulnerabilities. I hope you enjoy. A little bit about me. I am a threat intel specialist with TD Bank here in Canada. Let me give a shout out to my awesome team that I'm very lucky to work with. I'm also a founding member of the Diana Initiative, supporting diversity and equality in our field. I'm very grateful to the terrific staff, volunteers, and supporters who helped make another wonderful online event happen this year. And I hope you can join us in person next year. Obligatory disclaimer time. The views expressed here today are mine alone and not those of my employer. So let's get started. As the saying goes, you don't know what you don't know. And with this talk, I want to show you how that really applies to the Internet of Things, or as we call it, IoT, and the insecurity and risks from mass embedded vulnerabilities. I'd like to give you some takeaways to better understand IoT in enterprise environments in terms of definition, threats, and attacks. And also give you some recommendations so that you can better secure what you have in place and enhance your current security policies. Let's start with defining IoT. Consider these to be points of ingress that can lead to further access. Now, there's a lot of IoT interpretation out there, and it kind of looks like this. But simply put, IoT devices are typically items not designed for the internet that have been enabled to connect, so that they can communicate with other devices. IoT in any flavor means extending internet connectivity to physical devices, ordinary objects, and IoT comes in different flavors. There's enterprise IoT, industrial IoT, Internet of Health IoT. This is tech that communicates machine to machine or mobile to mobile. So what we're doing here is expanding beyond our defined security and monitoring perimeters to connect physical devices that were not originally designed to connect. And we're adding digital intelligence to enable communications and then taking us, the humans, out of the equation. In that sense, we are handing over our control to the machines. Let me leave that with you. Okay, when you add IoT into your enterprise environment, you get, ta-da, the enterprise of things. And that's what happens when we bring all the things that connect into organizational networks. Now, much of it is related to operational tech, or OT, tied to achieving the goals and outcomes of a line of business. Many IoT devices are unmanaged systems that can communicate with other devices and systems in your organization. They process and transmit information. They have an operating system, no matter how simple that is, but they cannot be managed via traditional security tools. They don't let us configure them to be better. We're stuck with what we get. And those unmanaged endpoints don't really have any built-in security that we can manage. Think plug and play. Convenience, my friends, has become the root of all evil. So when IoT becomes EOT, that attack surface increases, and so does our liability. It's everywhere. In manufacturing, there's automation. Sensors and scanners, robots on the manufacturing floor. In healthcare, they use it to cut costs and improve the quality of care for patients. There's remote patient monitoring, telemedicine, pumps, MRI machines, patient monitors. In fact, there can be as many as 15 connected devices per bed. Now, there have been some excellent talks about IoT in medical devices and the security risks associated. Let me give a shout out to the members of I Am the Cavalry and the very important work that they've been doing. Now, businesses and corporations use smart TVs and digital conferencing, as well as printers and scanners. Retail uses it everywhere it can. There's beacons that push out messages at the point of sale, automated checkout kiosks, which are showing up increasingly, inventory management through smart shelves, tracking or monitoring for theft, and digital displays. Transportation and logistics use sensors for warehouse management. They use it on vehicles to help track the locations or for fuel consumption, for delivery times, and to reroute vehicles. And then there are wearables that allow workers to communicate with their colleagues. In buildings and facility management, there's security, webcams, locks, lighting, and HVAC systems. That's a whole lot of vulnerability just waiting to happen. And then COVID-19 happened. Now, a new study by Zscaler looked at IoT devices that were left on corporate networks during the pandemic. 575 million device transactions and 300,000 IoT-specific malware attacks were blocked over a 2-week period in December of 2020. That measured as an increase of 700% from pre-pandemic levels, and the attacks targeted 553 different types of devices, all connected to and communicating with corporate IT networks, while the workforce was remote. So 76% of these devices were communication on unencrypted plain text channels. Let that sink in. That's a majority of IoT transactions, and it poses a significant risk to the organization. The highest traffic came from manufacturing and retail industries, with 59% of transactions measured. Enterprise was second with 28%. Healthcare was third with 8%. Expect the unexpected. There were smart fridges and musical lamps sending traffic through corporate networks. Do you know what's on your network? So what could go wrong? Well, think refrigeration on trucks. The temperature control fails. The sensor does not alert. Valuable cargo spoils. That's money lost. And let's talk about something bigger. Think HVAC systems anywhere we work, live, or stay. What if there was an outbreak of an airborne contagion like Legionnaire's disease? Think quality control that regulates the safety of what we eat or what we use. And if those are tampered with, would we know? If somebody changed the settings just enough, how would we know? Call me paranoid. We rely on these devices to be reliable, to notify us. We trust them. Let's talk about the architecture. There are a lot of protocols involved with all of those connections. And even if these are just simple devices doing one task, we're going to talk now about why understanding the vulnerabilities in these protocols matters. Because embedded devices. These are the 4 communications architectures used. There's device-to-device, so that IoT devices within the same network generally connect using wireless PAN protocols, like Bluetooth and Zigbee. There's device-to-cloud. IoT devices connect directly to the cloud. Typically, they use a long-range communications network such as cellular. And then there's device-to-gateway. These architectures transfer information from sensors to the cloud via a gateway device which collects the data and then communicates it to the cloud through additional network connectivity, like Wi-Fi or cellular connections. And then there's cloud-to-cloud. This is also known as back-end data sharing, and it enables third parties to access uploaded data from IoT devices. For example, smart buildings receiving data from smart thermostats and smart light bulbs, which can send the data to the cloud via Wi-Fi. Now, there are wireless sensors and actuators which provide the connection between the digital and physical worlds. They work together to produce and collect vast amounts of user data. The actuators can produce physical changes based on the data that they get from the sensors, and they can shut off a device or move equipment. Think back to how we were talking about handing over control to the machines and what could go wrong? IoT devices can be grouped according to the type of connection they require. Devices which need a lot of range and bandwidth would use cellular or satellite connections. For things that transmit small amounts of data, the best option is to have an LPWAN or low-range WAN connection. These technologies offer less bandwidth, but they make up for it in terms of energy efficiency. Manufacturers can also choose between Wi-Fi, Bluetooth, or Ethernet connections, and these standards provide more bandwidth, but at the cost of shorter range. There's System on Module, or SOM, which integrate a system function into a single module. This brings simplicity and intelligence to an embedded IoT system with reduced power. For IoT applications, integrated wireless connectivity enables broad deployment in numerous scenarios. The low power consumption is a high priority. One of the benefits of SOMs is that they can reduce the time and cost to develop a PCB-based design. Then there's also a single board computer, or an SBC, and that provides an entire computer built on a single circuit board. It'll include microprocessors, memory, input-output, and connectivity. But it's not a desktop personal computer. It doesn't have expansion slots. Now, some of these can even offer pre-certified Wi-Fi or Bluetooth connectivity. They even, in some cases, can offer enterprise-level security. For the architecture, let's make it simple and talk about it in terms of the 3 layers. First, there's the physical layer. This has the sensors, actuators, smart devices, the things. They are at the edge of the IoT network, or edge nodes, and they interface and communicate to the cloud via wire or localized radio frequency RF networks, and this is done through gateways. Now, some will come internet ready right out of the box and require little or no configuration. Then there's others, older or legacy items, and they use conventional methods like analog or serial connections. These conventional devices get connected to microcontrollers, systems on modules, the SOMs, or single board computers, the SBCs that we talked about, via Arduinos, NetBurners, or Raspberry Pis. And you're probably familiar with those. Next are IoT gateways. These act as your middlemen. They're the messenger and translator between the cloud and the smart device clusters. Gateways are not always cloud, however. Physical devices or software programs will run from the field and in close proximity to the edge sensors and other devices. Their job is mostly to normalize, connect, and then transfer data between the physical device layer and the cloud. And they can also support additional computing and peripheral functions such as telemetry or multiple protocol translation, pre-processing, filtering massive raw sensor data, provisioning, or device management. And last is the application layer, or the cloud. It communicates with the gateway by the internet or wired or cellular connections. A lot of raw data is being collected by all of those sensors, and it's going to need a lot of processing power and space. This is more complicated than we realize. This diagram can depict for you the data and control flows that are based on usage across enterprise systems, spanning the 3 networks that are shown here, with 3 tiers. There's edge, platform, and enterprise. Essentially, these are things talking to things, and the devices are on the far left. The protocols are in the middle and are likely the vendor of the item. We, the enterprise, talk to the vendor. And on the right is us, the enterprise customer consuming that data, video streams, sensor logs, etc. So, to recap, there are 3 layers. Billions of physical devices, some of which can produce physical changes. We're monitoring the data flow across 3 networks. And there are challenges integrating IoT into established enterprise networks. So how is it that IoT attacks differ? Well, let's start with this. Let's be clear. Hyperconnectivity. In the rush to market, we overlook security in the software-defined lifecycle. So devices get shipped that cannot be updated, or with limited capacity to be updated. And as IoT moves into a range of enterprise environments, driven by consumer demand and BYOD desire, Shadow IT becomes Shadow ET, and it brings new challenges and risks that our existing compliance and security don't address or regulate. Now, most organizations still don't inventory IoT devices because they don't have centralized control over what IoT devices and apps are in their workplace. How are you inventorying the personal devices used by staff? Is it BYO IoT? Risk gets pushed along the supply chain so that whoever buys it owns it. Let's apply the CIA triangle: confidentiality, integrity, and availability. We're used to attacks or breaches being primarily focused on data exfiltration for identity theft, credit card fraud, ransomware, etc. That's confidentiality. Now, in the IoT world, there's some of that, but connected devices have more riding on them. They run things that we need and rely on. Attackers turn devices against the company. So it's more about disruption or even destruction. And impact is measured in damage that becomes dollars. This becomes availability or potentially integrity. And attackers can carry out man-in-the-middle, spoofing, cloning, or software attacks to steal credentials. As an example of an attack, in April 2019, Microsoft's Threat Intelligence Center discovered a targeted attack by Strontium, or APT28, against IoT devices. The plan was to use compromised IoT devices as access points into the broader corporate network, and there were attempts across multiple customer locations. They tried exploits against a VoIP phone, a printer, and a video decoder. Now, 2 of the 3 devices still carried factory security settings, and the software in the 3rd had not been updated. If we take a look at our wheel of misfortune, breaches resulting from unsecured IoT devices increased by 26% in 2020, up from 15% in 2017. These devices can collect very sensitive data. Connected devices are always communicating with other devices on the network. According to Palo Alto, 98% of enterprise IoT communications are in plain text, unsecured. Now, IoT devices are low-hanging fruit, and 57% are vulnerable to medium or even high severity attacks. 83% of medical imaging devices run on unsupported operating systems. And to illustrate the effect of an IoT attack within enterprise systems, I give you Polycom. Because doesn't every organization have teleconferencing? And a lot of them have Polycoms. Now, there are a lot of endpoints in these systems, and they each have their own security and risk factors to consider. More importantly, every single endpoint presents an opportunity to get into the network. So who actually implements these? Very likely, it's the nice folks in AV, but I don't think they're thinking about security when they're setting it up. Now, this is about an attack on the Polycom HDX video conferencing systems that was discovered by Omni in August of 2018. Thousands were exposed externally and many more were deployed internally. Polycom systems are linked to each other across different corporate offices globally. At the time, a trio of IoT botnets, named Bushido, Hades, and Yahweh, which were based on a Mirai variant, were targeting vulnerable devices. They spread by telnet, they used brute force for access, and they were looking for BusyBox, wget, and other binaries on those Linux operating systems. It just takes one exposed, misconfigured system to infect the network. Add to this the risk of unified communications devices that have default passwords or PINs. Yeah. So, let's do a recap. This is not the same old, same old. We need to evaluate what we've got in place because attackers can leverage and pivot, and each endpoint becomes a point of ingress for further access. You can't secure what you don't know. Default configurations. Have you looked for undocumented backdoor accounts? Misconfiguration. What do you have turned on by default that exposes you and could be turned off? Universal plug and play or open ports. And what are the firmware update policies for these devices? Can you get automated updates? Network segmentation for the win, because we can do this better. Okay, let's talk about those attacks. A series of massive vulnerabilities starting in 2019 that were identified. Now, taking action to remediate is hard. Device vendors would need to take the updated TCP/IP stacks and integrate them as firmware updates into their products. The thing is, many vulnerable devices don't even ship with the ability to update the firmware, meaning that some equipment will most likely remain vulnerable for the rest of its shelf life. And this is what I wanted to share with you today, because this is truly a series of unfortunate events waiting to happen. Our story starts here with Urgent 11, July of 2019. A set of 11 vulnerabilities which affects the TCP/IP stack in VxWorks known as IPNet, the most widely used operating system that you've probably never heard of. 6 of these are critical and can enable remote code execution. There's a wide range of affected versions spanning 13 years. Now, how many manufacturers use VxWorks? Well, it's found in over 2 billion devices. Attackers can circumvent the network address translation, or NAT, and firewalls to control devices remotely via flaws in the TCP/IP stack. Undetected, with no user interaction required. And the vulnerabilities have a low-level position in the stack so that attacks are viewed as legitimate network activity. And since the vulnerabilities don't require any adaptations for the various devices using the network stack, this spreads very easily. This affects real-time operating systems that are used in countless critical infrastructure and manufacturing devices and settings. You'll probably recognize almost all of those labels. In an example of an attack, VxWorks devices are at the perimeter of the network. Firewalls. Now, you would expect these devices to be designed to fight off incoming attacks, and they should be secure. However, an attacker could take over the SonicWall firewall on the perimeter via the Urgent 11 flaws and an internet connection, using a specially crafted TCP packet, and then take over all the firewalls to build a botnet. Now, this might sound pretty extreme, so I've put the URL up on the bottom so that you can watch Armis's video of the proof of concept. Ripple 20, June of 2020. Now, this was named for the ripple effect of one vulnerable component spreading out to impact countless more. These are 19 vulnerabilities that impact a TCP IP library known as ThroughTek, which was developed in 1997, and that is in the base of many IoT products. It enables devices or software to connect to the internet via TCP IP connections. There are 6 critical vulnerabilities that can enable remote code execution. And this impacts hundreds of millions of things. We're talking smart home devices, routers, communications equipment used for mobile and satellites, or data center equipment. And this is found in healthcare systems, transportation systems, and power grids. In an attack, they could steal information from a printer, mess with an infusion pump, hamper industrial control devices. An attacker could hide malicious code within embedded devices for years, and one of the vulnerabilities could enable entry from outside into the network boundaries. Yes. AMNESIA 33 from December of 2020. This was discovered by Forescout while they were doing research on Project Memoria. And they were doing Project Memoria because of what had been revealed about vulnerabilities in the IPNet and TCP/IP stacks from Urgent 11 and Ripple 20. So I want to call out the importance of this research and give a big thanks. There were 33 vulnerabilities that impact firmware identified, and this affects 4 open source TCP/IP libraries. The affected libraries were added to device firmware to allow products to support TCP/IP, which is the current most widely used networking communications protocol. Now, there were 4 critical memory corruption flaws. And that poses a greater risk to our work from home world, because while the endpoint is easier to compromise, this then increases the risk that unmanaged home routers could compromise VPN protected networks and potentially gain access to the corporation. If exploited, an attacker could, among other things, perform remote code execution to take control of a target device, denial of service to impair functionality and impact business operations. There could be an information leak and acquire potentially sensitive information. There could be DNS cache poisoning attacks, which point a device to a malicious website. And that brings us to Numberjack from February of this year. Numberjack adds 7 more vulnerable TCP/IP stacks to the 4 open TCP/IP stacks that were identified in AMNESIA 33, increasing the vulnerable devices by millions. In February of 2021, Forescout reported on vulnerabilities in multiple TCP/IP stacks that impact the generation of initial sequence numbers, or ISNs. Now, this is a 32-bit number used in establishing new sessions within TCP connections. And to illustrate in a similar concept, let me take a moment and remember the legendary work done by the late, great Dan Kaminsky. He identified that initial sequence numbers were not sufficiently randomized in DNS queries back in 2008 and effectively prevented a major situation, essentially saving the world. It's a great story and you should read about it. So ISNs must be randomly generated to ensure that TCP connections between devices are unique, that there are no collisions, and to prevent a third party from interfering with an existing connection. Because if an attacker can guess an ISN, they can potentially hijack an ongoing connection or spoof a new one. And these vulnerabilities may not be as critical as those identified in AMNESIA 33, but they're easier for attackers to identify and more likely to be exploited, leading to a denial of service attack, authentication bypass, or malicious code injection. The popularity in some use cases of the vulnerable stacks is extensive, because these are used by millions of devices and include everything from file servers to embedded components. Identification is a challenge because you don't often know what stack a device is running. And as you'll hear me say repeatedly in this talk, embedded devices are very difficult to manage and update. The vulnerabilities were discovered and disclosed to the manufacturers in October of 2020. Now, in a possible attack, the attacker would impersonate a legitimate client and open a connection to a server using a deterministic ISN generator. The server would think that the SYN packet is coming from a client and then send a SYN-ACK packet to the client, which includes the ISN. Now, the attacker can't see the SYN-ACK packet sent to the client, but if they're able to guess the value of ISN, then they can still send an ACK packet back to the server with the guessed ISN used by the server and complete the three-way handshake. And so the server thinks it has a legitimate connection with the client, when it's really communicating with the attacker. NameRec from April of this year. This is from a joint effort by Forescout and an Israeli firm, JSOF. 9 vulnerabilities affecting the implementation of the domain name system protocol in several major TCP/IP network communication stacks. There's FreeBSD, vulnerable version 12.1, and one of the most popular operating systems in the BSD family. There's IPNet, vulnerable version VxWorks 6.6, which is now under the Wind River maintenance and used by VxWorks real-time operating system. There's NetX, vulnerable version 6.0.1, which is part of the ThreadX real-time operating system and now an open source project maintained by Microsoft under the name Azure RTOS NetX. And there's NucleusNet, vulnerable version 4.3, part of the Nucleus real-time operating system maintained by Mentor Graphics, which is a Siemens business and is used in medical, industrial, consumer, aerospace, and Internet of Things devices. These affect at least 100 million devices. Now, there are a number of bugs that could be combined for serious impact. Attacks could involve stealing sensitive data, or modifying or taking equipment offline for sabotage purposes. Attackers could cause serious damage to government or enterprise servers, to healthcare facilities, retailers, or companies in the manufacturing business. They could also tamper with critical building functions in residential or commercial locations to control the heating and ventilation, to disable security systems, or to tamper with automated lighting systems. REALTEK from April of this year. So, the REALTEK Software Development Kit, or SDK, security flaws in their RTL 819XD chipsets affect Wi-Fi devices. A lot of Wi-Fi devices. These are used by over 65 IoT device manufacturers, 200 IoT product lines, and hundreds of thousands of devices. There's routers, cameras, and a whole lot more. This involves 4 vulnerabilities. There's a stack buffer overflow via universal plug-and-play, a heap-based buffer overflow, a command injection, and saving the best for last, there are multiple vulnerabilities in the web management interface, which has the most serious one. Via form sys command, a remote, unauthenticated attacker could execute arbitrary command at the highest level of privilege. So, if we wanted to look at an attack here, an attacker could gain control of a wireless router for full compromise. And as per the quotation, given that wireless routers are a central node for many devices, well, the compromise here would spell disaster for all of those other devices connected via the home or workplace networks. Arcadyan, from August of this year. You probably haven't heard of it, but now you will. Arcadyan firmware is found in many SOHO or small office home office routers, notably the Buffalo brand. CVE 2021-20090 existed in Arcadyan's firmware for at least 10 years. It is a path traversal vulnerability discovered by Tenable researchers, which leads to an authentication bypass, and when exploited, the attacker can take over control of the affected device. The vulnerability is described by Tenable as trivial to exploit. That means that every vendor who's used it in their models has automatically inherited the bug. It affects millions of devices from 20 vendors, including internet service providers. Now, it was first identified in those Buffalo routers, but it's been seen in routers supplied by ISPs such as British Telecom and Deutsche Telekom to their customers, and includes brands such as ASUS. Now, according to Tenable, the vulnerability exists due to a list of folders which falls under a bypass list for authentication. For most of the devices that are listed, that means that the vulnerability could be triggered in multiple ways, and the devices impacted by the vulnerable Arcadyan code could be leveraged to access other devices on a home or corporate network, or manipulate DNS records to serve users up with some malicious content, even without an additional vulnerability to grant root access. There were a series of attacks earlier this year, spreading from February, then again in June and July, and then again in August, which were targeting vulnerable routers to deploy a Mirai botnet variant. And security researchers have warned that, quote, given that most people may not even be aware of the security risk, and they won't be upgrading their device anytime soon, this attack tactic can be very successful, cheap, and easy to carry out. Here is Tenable's proof of concept for the Arcadyan flaw. Now, for me, this highlights the risk through IoT of supply chain compromise, a code base with vulnerabilities, numerous vendors who then embed it in their systems, distribute it, and it gets sold to customers globally. Tenable calls this out in their white paper, Router Vulnerability Present for a Decade, citing, quote, the vulnerabilities discovered in the Arcadyan-based routers and modems serve as a small case study in how flaws affecting a shared library can become increasingly difficult to report, track, and fix due to the number of vendors involved. Furthermore, with each new vendor found to be downstream of the vulnerable link in the supply chain, the attack surface area increases exponentially. And then there's ThroughTek. There was a lot going on this August. Nozomi Networks announced the discovery and disclosure of a vulnerability in security cameras from a software component supplied by ThroughTek. This was identified as a critical vulnerability, an improper access control flaw. The KLA peer-to-peer software development kit provides remote access to audio and video streams online. It's built into client software and networked IoT devices. There are potentially 83 million of them. So that makes it hard to actually trace back because software supply chain issues. And this was part of the supply chain for many OEMs or original equipment manufacturers for security cameras and IoT devices. And the risks of vulnerable cameras are unauthorized access to confidential audio and video camera feeds, which could reveal sensitive data. In this case, the attack is unauthorized access to remotely compromise the device and then watch real-time video data or listen to live audio and potentially access sensitive data. In another attack, this will show how a remote attacker could gain unauthorized access and then get the device credentials to be used in further attacks for more control. Then in September, we had BrakTooth. 16 vulnerabilities across 13 Bluetooth chipsets, and these were discovered by the Automated Systems Security Research Group of Singapore. 1,400 products from 11 vendors, including Intel, Qualcomm, and Texas Instruments. The most severe of these was identified as CVE 2021-28139. It affects the ESP32 system on chip widely used in many Bluetooth-based appliances. It's cheap, low power, Bluetooth and Wi-Fi, and it's everywhere. No previous pairing or authentication required. The impact is either a crash or a deadlock. Now, there have been some other vulnerabilities impacting the Bluetooth protocol and its implementations over the past 2 years. And they include Blurtooth, Knob, Bias, Blesa, and Swaintooth. In an attack, due to the lack of out-of-bounds check in the library, an attacker could inject arbitrary code on a vulnerable device and erase the NVRAM data. Any of the attacks could be done using a $15 Bluetooth USB radio kit, shown in the examples. Now, the researchers tested products from 11 vendors and gave them over 90 days warning, but not all the vendors got patches out in that time. As of September the 1st, Espressive Systems, Infineon, and Bluetrim released patches. Texas Instruments said no. The researchers won't release a proof of concept to reproduce the attacks, but they have a web form where vendors can contact them and then get code to test for themselves. I've put the URL on the slide at the bottom. So, what have we learned? We've learned about a series of widespread vulnerabilities related to TCP/IP stacks, and that the flaws in these stacks are inherited in software used in embedded devices. That there is a real problem of identification. How do you know if it's in your device? That embedded devices are difficult to manage and update. And yes, attackers are actively searching for vulnerable, unpatched devices to exploit. So what can we do about this? Well, there's some good news. There's some progress that's been made. In January of 2020, the California IoT Cybersecurity Improvement Act from 2017 took effect. They were the first state to adopt an IoT law. Oregon followed soon after with their own bill. Now, manufacturers of IoT devices are required to equip any IoT device that they make with a reasonable security feature appropriate to that device, the information that it may collect, hold, or send, and to protect the device and information on it from unauthorized access, destruction, use, modification, or disclosure. In December of 2020, President Trump signed into law the IoT Cybersecurity Improvement Act, and this provides the first federal standards for this area. NIST was mandated to develop minimum cybersecurity standards for any internet-connected device sold by vendors to the U.S. government and IoT vendors to create vulnerability disclosure policies to promptly inform. We need to put some rules in place. We need to automate the identification of IoT devices so that we don't have to play hide and seek anymore. We should use device classification to understand how, where, and why they are used, and then know how they can be manipulated. We can use frameworks from NIST and CIS to enforce them for unmanaged devices and IoT. We need to have IoT policies and compliance functions, and we need to design with security from the beginning. IT, OT need to work together on this, with clear roles to manage applications, systems infrastructure, and data. We need to have a mature software-defined lifecycle and have security champions, involve the code developers, build standards and baselines, and eliminate special snowflakes, and leverage the power of the BOM, the bill of materials. Have bills of materials for all the things. And this, please, because you don't know what you've got till it's pwned. So what can you do? Here are some suggestions. Know your attack surface. Use multi-factor authentication. Segment your network. Keep your firewalls and your VPNs up to date. Automation is your friend. Have centralized access logs. Use behavioral monitoring to check for anomalies. Zero trust. And as a final takeaway, spend some time and money because a culture shift is needed. We need to break down the silos within and between IT, security, and other departments to ensure visibility and understanding. Our shared goal should be this: building a cybersecurity strategy across departments and functions. Let me reference the movie iRobot. In a society that embraced handing over tasks to tech, things were good until they weren't, which about sums up what it's like when IoT infiltrates enterprise. These devices are not the obedient little soldiers that computers and laptops are. These interact differently with the existing network. They behave differently. They operate with little to no human intervention. Automating convenience with inadequate supervision is going to end badly. Just saying. And with that, thank you so much for your time and for attending my talk. I hope it was helpful. And if you have got any questions, please feel free to contact me here. Thank you so very, very much.